Oh, well, thank you all very much for coming, and a Happy New Year to all of you. I think we'll make a start. After all, you're not here to enjoy yourselves, are you? Well, today I want to talk about the famous French mathematician and physicist Jean-Baptiste Joseph Fourier and some of the consequences of his mathematical investigations into the conduction of heat. On a very cold winter's day, I think talking about the conduction of heat should be quite a good topic. So he derived an equation, not surprisingly called the heat equation, to describe the conduction of heat, but more importantly, really, an approach to solving that equation, the heat equation, by use of an infinite series of trigonometric functions, now called Fourier series. And the ideas he introduced had major applications in other physical problems and also led to some of the most important mathematical discoveries of the 19th century. And some of them I'll be mentioning in my lecture after next, and Cantor and Infinity. So let me start my overview of the lecture by talking briefly about the situation in mathematics and its use in explaining and predicting the world about us at the end of the 18th century. Well, during the 18th century, many master mathematicians, for example, Laplace and Lagrange, had built on Newtonian mechanics to describe and predict the motion of bodies on Earth and in the heavens, in the sky. And they had the underlying equations of the motion of bodies. Indeed, they had them in many different formulations, and they investigated these equations mathematically. However, the behaviour of heat, light, electricity, and magnetism had yet to yield their governing equations. And this lecture is about applying mathematics to one of those four areas, namely heat. And it was Joseph Fourier, who was a distinguished mathematician, physicist, but also Egyptologist, demographer, and public servant, who tackled the conduction of heat, and as I've said, developed methods for solving them that were of lasting importance. So let me start by outlining Fourier's rich and dramatic life and some of the events of the turbulent times in which he lived, centering around the French Revolution. Then I'll consider his work on the conduction of heat and motivate his derivation of the heat equation and his use of trigonometric functions in its solution. Then I want to look at some case studies involving approximation by trigonometric functions, on tide prediction, and on the magnetic compass, both involving William Thomson, Lord Kelvin. Kelvin was also involved with the successful transmission of telegraph signals under the underwater Transatlantic cable, and that will bring us back to the heat equation, because the heat equation approximately models pulses of electricity going through an underwater telegraph cable. And finally, I'll finish by looking at some current applications. So, something about Fourier. He was born in Burgundy, 1768, the son of a master tailor. His mother died when he was 9, and his father shortly afterwards. However, he had an outstanding school career, particularly in mathematics. And at about the age of 17, he applied to the military of war to join the artillery or the engineers. But his application met with the crushing reply that as he was not of royal blood, he was not acceptable, even if he were a second Newton. Fourier then decided to enter the church, and in 1787 joined the Benedictine teaching order to prepare for his vows, and he was also a professor of mathematics for the other novices. However, the outbreak of the French Revolution and its constantly changeable developments and factions was a dramatic influence on Fourier's life. And in a letter written later from prison in justification of his part in the revolution in Auxerre in 1793 and 1794, Fourier describes the growth of his political views. He said, "The first events of the revolution did not change my way of life. Because of my age, I was still unable to speak in public, and impaired by night studies, my health scarcely sufficed for the work my position required of me. From another point of view, I will admit frankly that I regarded these events as the customary disturbances of a state in which a new usurper tends to pluck the scepter from his predecessor. History will say to what extent this opinion was justified. Republican principles still belong to an abstract theory. It was not always possible to profess them openly." And the part I particularly wanted to share with you after that quote about not being of royal blood, even if he were a second Newton. He finished, or he continued, as the natural ideas of equality developed, it was possible to conceive the sublime hope of establishing among us a free government, exempt from kings and priests, and to free from this double yoke the long usurped soil of Europe. I readily became enamoured of this cause, in my opinion the greatest and the most beautiful which any nation has ever undertaken. And that was written during one of Fourier's many spells in prison. And on this occasion it appears that it was only Robespierre's fall that saved Fourier from the guillotine. Subsequently, Fourier went to Paris, first of all to study at the École Normale. However, he was again arrested, released, rearrested, and then following yet another change of political rulers, became a teacher at the École Polytechnique, where in 1797 he succeeded Lagrange in the chair of analysis and mechanics, and where he gained a reputation as an outstanding lecturer. His burgeoning academic career was ended, or at least interrupted, in 1798 by government orders to join as a scientific advisor the French invasion of Egypt, commanded by Napoleon. Fourier returned to France in 1801 and accepted an offer from Napoleon to become prefect of the Department of the Isère in southeastern France. He was an effective and well-liked administrator, organising the draining of swamps and supervising the building of the roads across the Alps from Grenoble to Turin. And at the same time, he was helping to organise the description of Egypt, a multi-volume work by the scholars and scientists who were on Napoleon's expedition to Egypt. Fourier wrote the General Introduction, a survey of Egyptian history up to modern times. And this work did much to arouse Egyptian interest in Egypt, European interest in Egypt, and help establish the subject of Egyptology. The other important lasting consequence of the expedition was the discovery of the Rosetta Stone. The decree on the stone is inscribed 3 times in hieroglyphic, suitable for priestly decree, in Demotic, the native script used for daily purposes, and in Greek, the language of the administration. And it was to provide the key for the deciphering of hieroglyphics. And the reason I'm mentioning it is that Champollion, who eventually deciphered the Rosetta Stone, was encouraged by Fourier to take up Egyptology. He took him under his wing and, in fact, protected him from conscription into the army. It was also while he was prefect that Fourier began his work on heat conduction. Fourier was unusual among mathematicians, very unusual, and having a distinguished non-mathematical career. This work on heat conduction was to fulfill his youthful ambition, which he hinted at a letter written much earlier in 1789, when he wrote, "Yesterday was my 21st birthday. At that age, Newton and Pascal had already acquired many claims to immortality." And I think I write that at every birthday, actually. But now, in his mid-30s, Fourier started on the work that was to bring him his immortality. So, during 3 remarkable years, 1804 to 1807, he discovered the underlying equations for heat conduction, discovered new mathematical methods and techniques for solving these equations, and applied his results to various situations and problems, and then used experimental evidence to test and check his results. The resulting memoir on his researches on the propagation of heat in solid bodies was initially not well received, and even though it formed the basis for Fourier's successful submission for an 1811 prize by the Paris Academy of Sciences, their report stated, referee's report, "The manner in which the author arrives at these equations is not exempt of difficulties, and that his analysis to integrate them still leaves something to be desired on the score of generality and even rigour." And although this report and the attitude of the referees Laplace and Lagrange to Fourier's submission, it's been severely criticised by many recent mathematicians, I think I agree rather with Tom Corner when he says in his really brilliant book on Fourier analysis, the quote from Corner is, "Laplace and Lagrange, the referees, could not see into the future, and their doubts are surely more a tribute to the originality of Fourier's methods than a reproach to mathematicians who Fourier greatly respected, and in Lagrange's case, admired." So, Fourier's main results were published in his 1822 Analytic Theory of Heat. This contained the first large-scale mathematization of a physical process that was not part of mechanics. It's one of its major importance in the history of mathematics. Final years of Fourier's life were spent in Paris, where he became part of the academic mainstream by then, to the extent of becoming secretary to the mathematical section of the Paris Academy of Sciences. And I'll just end this brief biographical sketch of Fourier with a comment by the distinguished historian of mathematics, Ivor Grattan Guinness, who died last month. And that's a picture of Ivor on the right. And one of Ivor's most important works was early in his career when he wrote on Fourier. And what he wrote about Fourier was the following, which does capture the essence of the man, because he survived a lot of the political turmoil by the support he had and for the people who risked their own lives to speak up for him, rather than by political manoeuvring. Ivor wrote, "He preserved his honour in difficult times, and when he died, he left behind him a memory of gratitude of those who had been under his care, as well as important problems for his scientific colleagues." So let me now turn to some of Fourier's work, in particular his main publication. The very first words in his analytic theory of heat of 1822 were, "Fundamental causes are not known to us. Fundamental causes are not known to us, but they are subject to simple and constant laws, which one can discover by observation, and whose study is the object of natural philosophy." And I want to pick out three things Fourier achieved. First, his derivation for the fundamental equation for the duction of heat and the resulting temperature distribution. And here we see on the bottom right, this is from on the right-hand side from a translation, English translation of 1878. We see the general equation for the propagation of heat in the interior of solids, and there it's given in 3 dimensions. I'm going to come back and talk a little bit about it in 1 dimension. On the top right-hand side is the first example of the use of trigonometric series in the theory of heat. And again, I'll come back to that later on. So that's the first thing he did, was the heat equation. The second thing that he did was the Fourier series that we see in the top right. And the third thing was the use of those Fourier series in order to be able to solve the heat equation. Okay. So let me first think about temperature and the flow of heat and illustrate it with an example. And as I promised in my last lecture, we'll return to a beverage-based theme. Last time it was about coffee cooling. This time it's where to store all that wine that you didn't drink over Christmas. So we want to build a cellar, and we need to decide on what depth it should be. Now, ideally, we would wish that the cellar, the temperature should be constant throughout the year, or whether it's summer or whether it's winter, or perhaps more realistically, that the temperature fluctuation should be as small as possible as the seasons change. Now, I want to give you, first of all, some qualitative arguments to show that that might be possible. And it's got to do with the passing of time. As time passes, heat will propagate through the ground. In summer, when the surface is hot, heat will propagate downwards. And in winter, when the surface is cool, heat will propagate upwards. But the heat needs time to propagate, so that, for example, when it's the hottest day of the year at the surface, it will not be the hottest day in the cellar, because there will be a delay as the heat propagates downwards through the ground to the cellar. We will see that the temperature in the ground and at the cellar, they're out of phase. That is, they peak at different times. If the depth is chosen correctly, we might hope, then there will be 6 months out of phase. That is, peak 6 months apart. Meaning that when it's hottest at the ground in summer, at the surface, it's coolest in the cellar, and when it's coolest in the surface at winter, it's warmest in the cellar. So that's due to the delay caused by the time it takes heat to propagate. There's another effect, which is that when the heat or cold eventually reaches the cellar, they produce a smaller change in temperature. They're attenuated or they're damped. That's because some heat is absorbed in the ground as it passes through. So the temperature difference in the cellar during the year will be less than the temperature difference at the surface during the year. Right, so there are qualitative arguments to say that the task should be possible, but how do you decide at what depth you're going to construct the cellar to achieve your objectives? And Fourier's techniques allow us to quantify that. And we'll see, or I'll illustrate or indicate, that it varies, of course, with the type of soil, whether it's clay or sand or whatever. But Fourier's techniques that with a particular type of soil, which corresponds to choosing the value of a particular parameter, that of a depth of about 4.5 meters, the change of phase is 6 months. So when it's summer at the surface, it's winter in the cellar, and vice versa. And at this depth, the temperature fluctuation during the entire year in the cellar is 1/16 of what it is at the surface. So if the surface yearly fluctuation is 32 degrees, then in the cellar, the temperature fluctuation will only be 2 degrees. So relatively small. All right, so let's go to work and start by finding the heat equation. We're going to do it in one dimension, but the same observational approach that I'm going to make applies in more than that. So we need some notation first of all, because it impresses people looking at the lecture. So we're going to denote, we're going to have one dimension. We're just going to move from the ground down vertically through the ground. And what we're going to denote the temperature at a point vertically down in the ground at depth x at time t by u of x comma t. So u is the notation for temperature. Now, the fundamental observation that we're going to use for getting an equation involving the temperature is the following. And it's not actually that surprising. It says that the rate of change of the temperature at depth x over time is the rate of change is proportional to the flow of heat into or out of x. So the rate of change of temperature at a particular point is proportional to the rate of flow of heat into the point. Right? More heat going in, the faster the temperature changes, and less heat going in, the less slowly the temperature changes. So we can express this in symbols as follows. At the top on the right, on the left-hand side, U again is the temperature. This du by dt, that expression up there, that's just the rate of change of temperature with time at a point x. So that's the rate of change of the temperature over time. And what we've got on the right-hand side, the K is a constant of proportionality depending upon the soil. So we'll have a value for it. It's got to do with the conductive properties of the soil, whether it's clay or sand or whatever. The other term, d2u by dx squared, well, that's the flow of heat into the point. And the reason it's the flow of heat into the point is that du by dx tells us the flow of heat to do with distance, and what we're looking at is the change of flow of heat. So change, whenever you see the word change, you know that you have to differentiate again, which is why you've got the second derivative there. Okay, so that's the equation that we want to solve. We want to be able to find an expression for u of xt in terms of x, in terms of t, that will tell us the temperature at x, at depth x, at time t. And that's the first idea. We now have the heat equation, and the observation that I mentioned will show you, how to get it in, with appropriate notation in 2 and 3 dimensions. So now the second main thing, and that's this idea of Fourier series. And what I'm going to do here is give an illustration, in fact, the very first one that Fourier gave himself in his analytic theory of heat, of being able to represent a particular waveform, the square waveform, which is in blue here. It's the one that's square. It only oscillates periodically between 2 fixed values. And it's also important these days in digital engineering. And I've given the first approximation to it here in Fourier series. I'll be coming to say later on how we calculate the Fourier series, but at the moment I just want to show you how they work and how effective they can work with only a few terms. So that's the first approximation, cosine of u, and that's the cosine curve there, and it's in red. And now I come to the second term, the second approximation rather, which is cosine of u minus a third, the cosine of 3u. And you can see about the way the approximation is getting better, drops down, getting better. Right? That's just after 2 terms. I always find this very surprising. This is after 3 terms, cosine of u minus a third cosine of 3u plus a fifth cosine of 5u. And really the approximation is getting very good indeed after just 3 trigonometric terms. And I only did one more to bring up the 4th term here. And you can see it, I think it's really rather nice. And in fact, as I say, I do find it quite surprising how well the square waveform only taking on two values and oscillating between them periodically, same length of time, is so well approximated by the first four terms of a Fourier series. Okay. The numbers here, a third, a fifth, well, 1, minus a third, plus a fifth, minus a seventh, they're called the Fourier coefficients. In other words, they're just the coefficients of the Fourier series representing the periodic waveform. And Fourier then went on to consider the more general question of which functions, which waveforms could be represented by a Fourier series, and also derive formulas involving integrals that allowed you to calculate the coefficients of the Fourier series. Right. And this generated lots of new mathematical activities, some of which I'll be mentioning in the lecture after next. So the first thing was deriving the heat equation. Second thing was getting these Fourier series in terms of trigonometric functions to approximate your function. For example, the change of heat at the change of temperature at the surface of the ground. But much of his success was really because of the fact that the heat equation, and indeed many of the laws of mathematical physics, are linear. And this just means that if you find two solutions to the underlying governing equations, then in fact you find many others, because, for example, their sum is also a solution. And I've illustrated this not with the heat equation, but with the wave equation. And every lecture should contain a picture of ducks, and this is my picture here. And what it's saying is that the waves caused by the three ducks, each duck will cause a wave pattern on the water, and if you want to find the wave pattern from all three of them, you just add them together. That's what I mean by linearity, by superposition, so that you can add the solutions together. And here I've just given some sort of classic examples with a one-dimensional wave here added onto this other one-dimensional wave down here, and they're completely out of phase, so they completely cancel to give you a stationary wave. And here we have two waves which are related to each other in that way. They're out of phase, and they add up together to reinforce each other. So in the first one, they cancel each other out. That was the word I was looking for. And here they reinforce each other. And here we've got two waves that are slightly out of phase, and they combine in that particular way. So this principle of linearity is very important because it allows you to build up complicated things from simple component ones. Right? And I just want to outline essentially how it's done here. Right? And so the core thing here is that if you can find U1 and U2 are solutions, then so is any linear combination of them. So alpha amount of U1 plus beta amount of U2 will also be a solution. Right? And the basic core ones that we're going to use are these trigonometric functions of sine and cosine. So what Fourier did was he represented the temperature distribution at depth x at time t in terms of these Fourier series, which involves sines and cosines. He plugs them into the equations, and the equation magically simplifies into a whole lot of simpler equations in the Fourier coefficients, which he solves to be able to get what the Fourier coefficients are. So the Fourier coefficients drop out. He doesn't know them completely because there's constants to be determined, but the constants are determined by the temperature at the surface. That's the boundary condition that you have. The fluctuation of temperature at the surface, they allow him to complete the complete solution, and it's because of that that we're able to obtain the quantitative result that I told you a while ago, that if you go down 4.5 meters, let's say, then the temperature is going to fluctuate very little and be completely out of phase with what it is at the surface. So I won't go into the sort of details of that there, but you've got the essential things to be able to recreate it for yourselves, I hope. Right. So what I want to do now is to go on to some other examples of approximating using trigonometric functions for various other practical circumstances, and by somebody who was very influenced by Fourier, and that is William Thomson, Lord Kelvin. And I want to look at some of his work and start off with his work on predicting the tides. Right? And this example, the reason I've picked it as well, is it will also show us how we can calculate the Fourier coefficients. So some of the things that I haven't said in the last few minutes, I'll now be showing to you in this other concrete example. So calculating the Fourier coefficients, we're going to be able to show how much of each trigonometric sine and cosine to use when we're doing an approximation. So first of all, let me give a little background about William Thomson. So he was born 1824, died 1907. He was a dominant figure in Victorian science, contributions to mathematics, physics, engineering, particularly in the areas of electricity and magnetism, and in thermodynamics, a branch of physics concerned with heat and energy, and also instrumental in the laying of the first transatlantic telegraph cable. Thomson was born in Belfast, although he's usually thought of Scottish, but I'm always very keen to tell people that he's born in Belfast, very close to where I was brought up. He was educated at Glasgow and Cambridge universities, appointed Professor of Natural Philosophy at Glasgow University at the age of 22. Remained at Glasgow until his death and was buried in Westminster Abbey alongside Isaac Newton. Very modest memorial. Well, Thomson was always a great admirer of Fourier, an admiration which went back to his youth. And Thomson tells the following story of when he was 16 on a family holiday to Germany, and I thought it was quite an appropriate one to take out. He says, going that summer to Germany with my father and my brothers and sisters, I took Fourier with me. My father took us to Germany and insisted that all work should be left behind so that the whole of our time could be given to learning German. We went to Frankfurt, where my father took a house for 2 months. Now, just 2 days before leaving Glasgow, I got Kelvin's book. Kelvin was a professor at Glasgow, and was shocked to be told that Fourier was mostly wrong. So I put Fourier in my box and used to go to Frankfurt, and used in Frankfurt to go down to the cellar surreptitiously every day to read a bit of Fourier. When my father discovered it, he was not very severe upon me. Not a problem many people have with teenage children, I think. And I also like the idea of Fourier being secretly read in a cellar. All right. So let me give an example of Fourier's influence on Thomson in the area of tidal prediction. All right. What Thomson did was to design a machine for predicting tides which computed the depth of water over a period of years for any port for which, quote, the tidal constituents have been found from harmonic analysis of tide gauge observations. And I'll show you what that means now. Calculating the coefficients of the trigonometric series giving the rise and fall of the tide. And Thomson used the lovely phrase, substituting brass for brain, when discussing the mechanization of tide prediction. I'll show you the machine a bit later on. So what I want to do is to show you briefly how to describe the tide, introduce the beautiful idea that allows you to calculate the amount of each trigonometric term that appears in that description, and then show his tide prediction machine. And the fundamental underlying cause of the tide is gravitation. The tide's caused by the gravitational pull of the sun and the moon on the oceans and on the rotation of the earth. But the exact pattern at any particular spot on the coast depends on the shape of the coastline and on the profile of the sea floor underneath, nearby. So even though the forces that cause the tides are completely understood, the tide at any one spot is essentially impossible to calculate theoretically. But what we can do is that we can record the height of the tide at that spot over a certain period of time and use these measurements then to predict the tide at that spot in the future. And I want to show you how that can be done. Right. Well, the tidal force is governed by a small number of astronomical motions which are themselves periodic. But their frequencies are not in a whole number ratio, so they don't ever repeat themselves exactly after a certain period of time. But there's an almost exact 19-year cycle in the joint pattern of the equinoxes and the solstices and the phases of the moon. So the tidal record repeats itself more or less exactly if you wait long enough for this period of 19 years. And that was used in predicting the tides at European ports. But a main motivation for Kelvin's work was predicting the tides in India, where they didn't want to wait 19 years for accurate tide predictions. And because the sun, the moon, the earth, earth, moon, sun are all in relative motion, the gravitational pull at a point in the ocean is constantly changed. And I've picked out the 5 main astronomical periodicities here. There's the length of the year, the length of the day, the lunar month, and the fact that the moon's axis changes, it precesses, the axis precesses, and the plane in which the moon revolves also precesses. And when you look at it, you see that the gravitational attraction can be described by means of sine functions. And I've here written down some of my favourite sine functions, where the frequencies are increasing as you go down the screen. But of course, these are also cosine functions if you move slightly to the right or the left in your seat, because sines and cosines are just shifted by a certain amount. So these are sine or cosine functions of increasing frequency as you move down the page. And what the analysis, what the geometry shows you, is that the height of the tide at a given place is of the following form. It's a sum of about 120 odd trigonometric terms. We know the frequencies V1, that's the multipliers of T. We know V1, V2, V3, V4, etc. What we do not know are the coefficients. We don't know the A0, the A1, the B1, the A2, and the B2. And I want to show you how we can find those from a historical record. So let me give you, I think this is a historical record coming up now. This is the weekly record of the tide in the River Clyde at the entrance to the Queen's Dock, Glasgow, and it's a weekly record, so there are one of these curves for each of the 7 days. So there are 7 of these plotting it. And the observations were obtained by another machine called the tidal gauge that Thomson created. Right. Now, 120 things are too awkward to deal with. 20 things are too awkward to deal with. I want to show you how we do it with just 2. So here I have, on the top left, it's a pretend tidal record. And it's made up of a composition of 2 trigonometric terms, an amount A of sine t and amount B of sine the square root of 2 times t. Right. And what we have to do is we have to find the A and we have to find the B. That's our task. We don't know, as it says there, how much there is of each of them. We do not know the coefficients A and B. And we use the following, I think, lovely idea. And here we have it. So we have on the top here, take our time over this here, we don't know A and we don't know B, but they've got some numerical values, and that's what gives rise to this curve up here. Now, what we're going to do is we're going to multiply this expression by sine of t, and when you do that, you get A sine t, sine t. Well, that's a squared term, sine squared term, and here you have a product of 2 sine terms with different frequencies. One of them the square root of 2, the other one is 1. If you now calculate the long-term average of this expression here, the B term will average out to give you 0. Now, the reason for that is that if you've got a product of 2 sine terms that are not the same, they can be written as the sum of 2 other sine terms. And if you take the average of a sine term over time, let me go back to here, if you take any one of these trigonometric functions and look at the average, which is finding the average as you're going along, because there's the same amount above and below the axis, the average is going to tend towards 0. So you multiply. If you want to find one of the particular terms, let me go forward again. Here we are. So we want to find the A term. So we multiply by this sine term here. We want to find the A term, so we multiply across by sine of t. This makes this term squared, so it's not going to average out to 0. But over here we have sine of the square root of 2 times t multiplied by the sine of t. The intermediary step I haven't written down is that this can be written as the sum of 2 trigonometric terms, and the average of a trigonometric term is 0. So doing this multiplication, calculating the long-term average, gives you what A is. Similarly, you just do it the other way round to find B. You multiply both the equation by sine of the square root of 2 times t, and this time it's the A term that averages out to give you 0. And I've written this in red because that's what the red one is down here, and when you do the long-term average, you find out that it's coming to give you the value 2, and the green one down here, when you multiply by sine square root of 2 times t, this is coming along to give you a value -3. So the actual values for A and B are A is equal to 2 and B is equal to -3. Now, if you've got the actual tidal record and you have down beneath it a trigonometric series and you're multiplying the two series together, there's an awful lot of work in that. And I won't show you, but one of the things that Thomson with his brother James did was to devise a mechanical integrator for multiplying those two series together and calculating what the long-term average was. Quite one of the first mechanical integrators, and they went on to develop other mechanical machines for solution of other very difficult problems as well. Really quite amazing. Right. So what we've got is we've got a tidal record from where you want to be able to predict the tides. We use this harmonic analyzer in order to obtain how much of each trigonometric term you have in the series. And now we want to be able to predict the tide in future. And this is where Thomson had the idea, travelling on a railway journey to attend the British Association meeting in Brighton in 1872. And if he had been travelling down from Northamptonshire today, like me, he would have had time to have devised many more machines apart from this one here. That's just telling you that what I'd done could be extended. And this is the tide predictor, and isn't it beautiful? What we have is over here we have wire, rope, whatever, and it's fixed. And then it goes over this pulley, under that one, over this one, under that one, over this one, over that one, over this one, over that one, over this one, over that one. This is very relaxing. Over that one, over this one. And I've got here a weight, but in actual fact, in the real thing, it was connected to a pen, and there was a rotating or a moving piece of paper that the pen was subscribing on. Now, down at the bottom, you've got the handle to crank, and important person was the person who turned the handle. And the handle is connected up to a gearing system, and the gearing is such that the frequency of oscillation of each of the pulleys, the gearing is set so that it will be one of the fundamental frequencies corresponding to the appropriate trigonometric term. They only did the 11 most important. 1, 2, 3, 4, 5, 6, 7, 8, 9. They only did that many. So what you do by the gearing down here, this is the frequencies. So they're hardwired into it, literally. And then the amplitudes, how far up and down these pulleys could move, so therefore what contributions they would give, they were the coefficients that had been calculated from the tidal record. So you turn the handle, the pulleys go up and down, the end result is the movement over here, and that's inscribed on a piece of paper, and that piece of paper can give the tidal record for a year ahead in a matter of hours. And this was used up to 1944. Here's a Kelvin tide predictor, a slightly later, slightly modified version of it. And here's the request for a most urgent 1943 note to Dudson from Farquharson, the Admiralty's Superintendent of Tides, listing the 11 pairs of the harmonic constants. They're the coefficients of the trig terms, and for which the request was to prepare the hourly tide for April through July 1944 to prepare for the D-Day landings. And this is, who's this here? This is Dudson up here, who was the Superintendent of Tides at the Liverpool Tidal Institute to predict the tides for the Normandy invasion. And it was only, it was only when digital computers came in the go that they mimicked this in software. Right. So again, building upon what Fourier, the point there was that wasn't a Fourier series. It was you could use the geometry to find out what trigonometric terms to put in. But this idea of calculating the coefficients is exactly what you do when you're calculating the coefficients of Fourier series, only you essentially do it by integration there, which is this business of finding the average. Right, now we give another just quick one here, because again it's such a nice one. I've been able to solve a very important problem, and it's Kelvin's magnetic compass. And the problem here was that when ships became made of iron and made of steel, while they were being constructed, when they were being constructed in dry dock or wherever you construct ships and there was a lot of hammering going on, it would pick up the Earth's magnetic field so that there would be a permanent magnetism within the ship, and that permanent magnetism would affect the reading of any magnetic compass that you were using on it. So the thing was, how do you compensate for the permanent magnetism of the ship? And what Kelvin did was to say quite nicely that what you can do is you can say that there's just an error term. There's a difference between the true compass reading and the displayed reading on the actual compass. So what you want to get and what you're actually observing, the difference between the two of them is the error term. Then he made an assumption, which can be reasonably justified, that the error term again is given by a trigonometric expression, a constant term, so much of a cosine, so much of cosine 2 beta, where beta is the displayed heading, sine beta and 2 beta. And then his resolution for that was that you take the ship when it's constructed and you point the ship in different directions and you observe different directions that you know. So you know what the correct direction is that you're pointing the ship in. You read what the compass is saying. So that gives you one equation because you can put that into here. You know what beta is, that's what's being read off the compass, but you know what the error is because you know the difference between the true direction and the error. So that gives you one equation for the A0, A1, A2, B1, B2. Then you point it in another direction and you do the same again, point it in another direction. So you end up with 5 equations with 5 unknowns. You're able to find out what the coefficients are, and then the last thing was to do the compensation for it, and he achieved the compensation by putting in magnets here, symmetrically placed. This is made of card in order that it should rotate very, very freely, and the strength of these magnets and the positioning of the magnets are in order to be able to give you the compensation that will negate that error term. And the compass made him a lot of money, was adopted by many navies, many admiralties around the world, except for the British, which was the one to adopt it last of all. They seem to be very, very conservative. All right, so the last real topic I want to mention has got to do with how to transmit signals over the transatlantic cable. Right. And the laying of the first transatlantic cable underwater, thought of the 8th wonder of the world in its day. And it's very hard to imagine, I mean, from our point of view, with mobile phones and for communication and with instant access to the web for information, what a dramatic difference the cable made. You know, before news took weeks to travel back, news and a response took weeks to travel back and forth to America. All right. And the first cable was laid in 1858, and although it soon broke down completely, it was able to, they were able to see how successful, how useful it would be, and eventually a working version was laid in 1866. Now, the shortest direct route is between the south of Ireland here, from Valencia Island, and this is a plaque here in the southwest of Ireland, to Newfoundland, and here's a sketch of Telegraph House at Trinity Bay in Newfoundland. Unfortunately, the shortest route turned out to be turned out to be suitable in terms of the profile of the sea, the surface of the sea, and not how there's a plateau which goes along here. Apparently, this line underneath it is giving the depth of the sea floor as you're going along. The other lines here, they're to do with the overground telegraph networks then in existence, and the lines here, the overground telegraph network then in existence. So we've got 2 types: telegraph wires overground, telegraph wires underwater. And I now want to consider what Kelvin contributed, because although laying over 2,000 miles of cable was that challenge enough, and it's a lovely story to read about, perhaps his greatest contribution was to the analysis of how signals propagate over an underwater cable and how to detect them. So let me share that with you. Just look at the left-hand side first of all. We've got a telegraph cable and we're trying to communicate over it, and we're going to communicate sending pulses, and there'll be some sort of coding in order to interpret the pulses, you know, Morse code or whatever. Now, the behavior of pulses going over a telegraph cable in air is very different from what happens in water, underwater. And in air, the transmission of the pulses is approximately described by the wave equation. And the thing about it is that an electrical pulse in a telegraph cable in air will travel with a well-defined speed with no change in shape or magnitude over time. There's a nice phrase I've seen describing. It's like a bullet going down the wire. All right, it stays with the same shape and it travels with a defined speed. And because of this then, the main limitation to the rate at which pulses are transmitted, that's going to be the limitation of your sending speed. How many pulses you can send per second. And of course, it's going to be dependent upon the receiving. How many pulses can be distinguished at the receiving end per second. But that's the main limitation on the rate at which you can send the pulses. On the other hand, for a cable underwater, the situation is very different indeed. And the behavior of a pulse being sent down a cable underwater is more akin, approximately described by the heat equation. And indeed, Thomson, coming back to Fourier, based his analysis upon the work that Fourier did upon the heat equation. And one of the reasons for this is that an underground cable, it has to be insulated from water, otherwise the signal would just leak away, and the water is an earth conductor. And what happens is that the pulse goes down the cable. The underwater cables not only conduct electricity, but it also stores it as it's passing. So an insulated underground cable has got what they call capacitance, the ability to store electric charge. And because of this, an electric pulse spreads out as it travels, and when it's received, it gradually rises, the pulse gradually rises, and then gradually decreases. And the longer the cable, the more smeared out the pulse will become. And I'd like to show you that analogy. I find it helpful to think of. It's as if between you and me, there's a long metal bar. And you're going to be the receiver, I'm going to be the sender. It's a long metal bar. I'm not going to use electric to send it, I'm going to use a blowtorch at this end. So I'm going to play a blowtorch along my end of it, and then the heat is going to go along the bar to your end. And you can see that it arrives at your end, it's very smeared out. It will arrive slowly, and when will the crest of the wave actually arrive? And when should I send the next pulse? By playing a blowtorch against the end of it again. And, well, part of what's happening is that the metal bar is storing heat as it goes along. So the pulse of heat is getting smeared out, and to a large extent, that's what's a good analogy, and Thomson loved analogies, so he might be proud of this one, of the analogy between electrical pulses in an underwater cable and heat travelling along a bar. But he analysed it quantitatively, and he came up with his law of squares. So our difficulty is, how often can we send a pulse so that they can be detected, so that they can be deciphered at the other end, distinguished at the other end? And he found out it could be described by a law of squares, and this just shows you how difficult the challenge was facing them. That if the cable length increases from 30 miles, say across the channel, which was a cable that was laid pretty early on, to 1,500 miles, which is not quite the distance across the Atlantic, well, to go from 30 to 1,500, that's an increase of 50. That's why I chose it, because it's easy to divide. But the retardation effects don't become 50 times as bad. They become the square of 50. They become 2,500 times as bad, which is a really dramatic degradation in the problem of receiving the signal at the other end. And crucial really to the eventual success of transmitting over nearly 2,000 miles of underwater cable was Thomson's invention of what's called the mirror galvanometer, which was a very sensitive instrument for measuring currents. It used the fact that the current would go through a little coil, a mirror was attached to the coil, a light was shined upon the mirror. Whenever the coil moved, that beam of light would be moved as well. It was very sensitive, very delicate, and it was able to detect the tiny and the blurred messages coming through the cable. All right. So to conclude then, really, what I hope you've seen is Fourier series can be used to represent a periodic function, for example, the square wave function, in terms of trigonometric functions, sines and cosine. And we've used it to help solve physical problems involving waves and the conduction of heat. And as I say, the question of what conditions can be imposed on a function so as to ensure that its Fourier series does indeed converge generated a lot of new activity. Now, the Fourier series I've mentioned were a way of decomposing a periodic function into its component harmonics or frequencies, and so indeed the subject is sometimes called harmonic analysis. Now, there are various ways of generalizing this idea, and there's one of which is looking at functions which are not periodic. The ones I've been considering up to now have been periodic. Ones which are not periodic, and representing and creating something called the Fourier transform, and that can be thought of as telling how much the original function has, how much it oscillates at all the different frequencies, but I didn't want to go into that. But it's a very powerful current mathematical idea with applications in diverse areas: probability theory, harmonic analysis itself, number theory, strangely enough. And it was used, for example, to prove the important result that every sufficiently large odd number is the sum of 3 primes. And if you look back to one of my other lectures in number theory, where I talk about this difficulty of being able to say the difficulty that arises because of the very different nature in numbers, the additive structure and the multiplicative structure are very hard to relate to each other. So this is telling us something about how a number can be written out in terms of primes using this idea of Fourier transform. All right. And then more practical areas, acoustics, signal theory, optics, computerized tomography, nuclear magnetic resonance, all of these imaging techniques, and crystallography are very much into and seem to inherently have to use ideas from Fourier transform theory. But let me leave the last word to Fourier and his view of mathematical discovery. And he said, "The in-depth study of nature is the richest source of mathematical discoveries. By providing investigations with a clear purpose, this study does not only have the advantage of eliminating vague hypotheses and calculations which do not lead us to any deeper understanding, it is, in addition, an assured means of formulating analysis itself and of discovering those constituent elements which will make the most important contributions to our knowledge and which the science of analysis should always preserve. These fundamental elements are those which appear repeatedly across the whole of the natural world." And what I hope to do today was to give you some practical illustrations of where you can use mathematics to make that kind of difference. So next time, come along when we'll be, please do come along, and when we'll be talking about Mobius and his band, and bring your Mobius strip with you, and we can all cut it up in different ways. And if you enjoy today's lectures, I often say do recommend to a friend, and if you didn't, then recommend it to somebody you dislike. Thank you.